fact, I did a poor job scheduling. This is a slot when they have these talks that occasionally some are required to come to. So I'll need to move my office hours next week, Wednesday, and I know this is the day the homework is due. So I wanted to kind of discuss it as a group. Probably all of you are the ones coming to class, so you're more on top of things. But you also get the benefit of taking part of this discussion. So the options would be where I can move them to would be from, they're usually 10 to 11 on Wednesday. I can move them to 9 to 10 o'clock on Wednesday. Also my lunch hour, noon to 1 is free. Do people have preferences? If my preference would be the 9 to 10 o'clock. So I'll do that unless I hear otherwise. In general, if this is a bad time, please let me know. I may need to I may need to shift this a few more times in the semester. Hopefully not on other times right on the day the homework is due. Because I know that's when you have the most questions. Also, I realize we haven't gone back to you on the project proposals yet. I think most of you have had questions. You've actually been able to talk to them in person, which is great. That works a lot better. We'll try and get those back by the end of the week. And then next week, I will discuss a bit more on the next step, which is the data collection report. Just what should you be doing for that? And again, it should not take too much time, but it'll take some time. Again, like the project proposal, that was there just so you're starting to think about these topics. So as you see the techniques in class, you can kind of have in mind, oh yeah, that would be a good technique for the project that we're thinking about. With the data collection report, for some people, they're going to be able to download data that's nicely formatted, and there's not all that much to do. For other people, this may take a long time, and maybe it takes a surprising amount of time, and you may not get everything done by the report, but at least you'll have gotten started on it. It's better doing it now than at the last minute, because then you won't get to do the fun stuff as much. Anyway, so I'll talk more about that next week. And finally, next week, Monday, there's no class. It's like, I think it's President's Day, right? So no class next Monday. Okay, so let's get into it. So the topic today is going to be assignment-based clustering, and so so the canonical example of this is the k-means clustering problem. So who's heard of k-means clustering before, and who's not heard of k-means clustering? Okay, so this is kind of one of the most common, famous kind of problems in data mining. So we'll talk about this, but then other variants and how they all interact with each other. Okay, so again, for these problems, we're given a set of data points. So this is a set of data points. And so often we can think of them as two-dimensional points in the plane, so we can draw pictures. And we're also going to have a distance that is defined in between these data points. And so in particular for the k-means clustering problem, we're going to specify specifically that X is going to be a subset of RD. So it's going to be, each of the points is going to be a vector in a d-dimensional space. And the distance between 2 points A and B is going to be exactly so it's exactly the L2 distance, the straight line distance between them. Okay, so for k-means, that's going to be the assumption. For other variants, we'll talk about this assumption here is not going to be needed. So we can go back to this general assumption. Okay, and so now the goal in this setting is to find a set of K a set of K centers. And these K centers are going to describe everything along with the D and the X as input, everything we need to know about the clustering. What differs in the different formulations, other than K-means, is going to be the objective that you want to solve for K. So with the algorithms we talked about on Monday, these hierarchical agglomerative clustering, we didn't really state what the true objective was. We didn't say we would like to find a solution which optimizes this problem. We just kind of said, here's a procedure of how you glue these clusters together. And then we kind of talked about which ones work for which situations. For the assignment-based, it's much more cleanly defined. So, so in particular for the K-means, okay, so in general what you want to do is to minimize a cost function on the centers that you found. So a set of K centers has to be a set C and the data function X. And the distance here is just going to be the data points X. And the distance here is just going to be implicit. Okay, and so what's common to all these is that we're going to use, we can kind of specify this a bit more. We're going to use this function, which is the nearest neighbor function. So this is going to be the arg min of an element ci in the set C of the distance between x and ci. Okay, so we have this assignment, and we're going to say that we have the set of centers, but we also have we're going to have K clusters, and these are the S1 through Sk, and so Si is going to be the subset of X such that phi of C of X is equal to Ci. Okay, so this is, so we're going to find the clusters based on these centers using this nearest neighbor function. Okay, so this was, we talked about nearest neighbors before in the distance. This is the nearest neighbor in the set C of centers to some data point X. It returns the center, Ci, which is closest to X. And then the clusters are defined as of all the data points such that their nearest neighbor is equal to center Ci of the clusters. Okay, and then these cost functions, this cost is going to end up somehow being, well, right there, some function of some cost hat function on Ci Si. Okay, so I'm going to somehow have some other cost function defined just between a cluster center and its set of points, and I'm going to combine these together. It's either going to be a sum or a max or something like that. So f will be a sum or a max, and this cost will somehow measure these cost functions again. So I'll go through examples really quickly, but before I do that, let me just draw a picture of how this clustering, you can think of this works. So our data points might be like this. Okay, and then we could pick our centers. So this will be C1, right? So the points in black here are X. this is going to be C2, and this will be C3. They might be data points, they might not be data points. And so then to do the assignment, we can draw the same thing we saw in the nearest near problem, this Voronoi diagram in between the cluster centers. Okay, so now the points in this cell, all the black points in here, their closest center is this one. All the black points in here, their closest center is this one, and the black points in here, closest center is this one here. Okay, so we have this Voronoi diagram again underlying what's going on here. And then the cost function will somehow define some pieces. So we're going to somehow say this is now cluster 2, this is cluster 1, and this one is cluster 3. And so the cost function will define some cost on each of these and either add them up or take the maximum. So then we'll apply a cost hash on each of these and then combine them together. That'll be our total cost. Okay. So now for the k-means formulation, we're going to say that cost of Cx is going to be the sum over x and x, the distance from x to phi of c of x squared. Sometimes the units are strange, so we'll take the square root here, but it's minimized the same way, so it doesn't matter so much. But it's looking at, for every data point, it maps to the closest center, and it squares that distance, and you want to minimize that. So this is the k-means clustering problem. Define the set of k centers, and you're given k as input, typically, somehow. And then you're trying to find a set C such that when you map everything to its closest center and you sum the squared distances of those, right? So in this picture here, I'm summing up all of these distances, and those distances squared. I sum all these up. And I do it for every point, right? So for every point, I map it to its closest center, and I square its distance. And so the sum of all these squared lengths is the k-means cost. Okay. Before we talk about how to approach k-means, there are some other useful variants, and you can, I tried to write it like you can write it in this way as well, where you can instead, and in some cases this will be useful. This is equal to the sum over Ci in C of the sum over x in Si right, so if I write it this way, it's still the sum of all the distances, because each point's distance is taken once. And because I sum over Si mapped to the centers, they don't need to have this phi function kind of calculated inside. But it's the same thing. Okay, so the other popular versions of this are the k-center problem. And this one, and we'll call this cost 2. This is going to be cost infinity. And this is going to be equal to the max of the distance between x and phi of c of x. Okay, so, and you can square it if you want to, but again, it doesn't make a difference. There's really no need to square it. But it's just the maximum distance. So instead, in this picture here, I want to look at all the edge lengths, and whichever edge length is the longest, that determines my cost. So I want every data point to be close to a center. Whereas the k-means is kind of averaging over them, averaging over their squared lengths. Say, why are you using the squared? Well, there's the k-median is going to be the sum of x and x of the distance x, phi of c of x. And this one's not squared. So the k-median is where you don't square this distance here. The k-means is usually much more popular than the k-median, and we'll discuss why that is. Even though it may seem strange that it's squaring it, but turns out that's going to be really helpful. Then there's another version that you'll, this is called the k-medioid, M-E-D-I-O-D, in case you can't read that. It's the same cost function as above. So again uses cost 1, but it requires that the center set is a subset of the data points. So it fixes that the centers are a subset of the data points. And so we'll see why you'd want to do that as well. It turns out that generally the squared on the k-means is there only for computational reasons. It makes the computation easier. There's some other reasons that if you're modeling data, you assume it follows some distribution, then maybe this is a little bit better. But this one is without squaring this one's going to be more robust. The k-means also, the main algorithm, which is called Lloyd's algorithm, that people typically use, requires this property I mentioned, that the distance is the straight line distance, is the Euclidean distance. So that algorithm requires it. If you drop that requirement, then you often are stuck with a situation where you only know how to compute centers which are of the subset of the data. And in that case, you probably want to use this formulation instead, because it's more robust. And then they're equally challenging to do. So that's why there's not kind of a cost 2 with the sum of the square distances where you make this requirement. You could do that also, but it's usually, if you're going to make this requirement, you might as well use cost 1 instead. Okay, so first of all, I haven't told you anything about algorithms yet, how you would do this. K-means is a problem description, is not the algorithm. The algorithm is we'll talk about next. Okay, so any questions on the clustering formulation?
What is the last one?
What's
the last one? K.
This is the k-medioid. Let me try and rewrite this. Is that more clear? That's a D. Okay. I wish I could write like a typewriter or something, but okay. All right, and this structure, this Voronoi diagram telling you how you decompose the points is that's going to stay fixed across these variants. All you need is the centers to tell you how the clusterings are formed. And so, so the only thing differing is the cost function, what you're trying to optimize. Okay? And so this is useful in a few ways. The centers give you some notion of a model. There's some underlying thing. You think the data points are close to the center. That represents all of the data points in the set, in the cluster, right? So all the data points in cluster SI are represented by cluster center CI. So you kind of are really kind of summarizing the data in this way. That the hierarchical clustering, it wasn't so clear it was doing that. Now, if the hierarchical clustering used the center as part of its approach, then yeah, you get the same property, but this is an inherent part of these techniques. Okay, so who has seen the common algorithm for k-means clustering, or called Lloyd's algorithm before? Okay. So for those of you who haven't seen this, how would you try and solve this k-means, find cluster centers to minimize this k-means cost function? What's the idea here? So it's kind of going to be for the. Actually, let's come back to the k-means. Let's come back to Lloyd's algorithm. Let's start with one that's even simpler. Let's start with the k-center problem. So this is often called the Gonzalez algorithm. Okay, so the k-center, remember, is minimizing the longest edge, the maximum cost. So let's start with this one. How would you try and find a set of centers that minimize the furthest edge? What's an idea? It's going to be really simple. Okay, how about I give some scaffolding here? So I'll just write out the algorithm. The first step is we're going to choose the first center, C1, from X, and so we're going to choose this one arbitrarily. So choose some element of the set X. So as we do this, we're going to maintain a set of centers. And so at first, we're going to say this set, this is an uppercase C, just contains one element, just the first center. Later, we'll have C2. So later, we'll have C2 equals C1, C2, and so forth. And Ci is going to be C1, C2, up to Ci. You guys, all right. Okay, so I have one center so far. Okay, so now how would I choose the next center?
Be the data point in the set furthest from that center.
Yeah, good. That's right. So that's basically the whole algorithm. You just have to repeat this. So let me put this inside of a for loop. So I equals 2 to k. Do set Ci equals to the R max of all the data points of our distance from X to its closest center of the centers we found so far. Okay, so in the first case, this is the set. Let me blow this up a little bit. This is phi of C, the set Ci minus 1, right? So this is the set of centers. This is C1, C2, up to Ci minus 1. So at this point, we're I is equal to 2, so the first round, this is just C1, which is just a single center. So it's just the point furthest from it. And so, after we found the first two centers, we picked the point that's furthest from either of those. Right? So the thing about the k-center objective is its cost is determined by a single point. there's one point which is the furthest away from one of its centers. And so we pick that point, because if we pick any other point, it might not decrease the overall cost. If we pick that one, it has to decrease the overall cost, because that one now is the distance 0. So now the next largest distance is either the same or smaller. The next largest distance is usually a nearby point to that one as well. Right, so this is the whole algorithm. You just run for k steps, and in each step you find the center furthest away from, you find the data point furthest away from all the existing centers. Right, so let's run through a small example algorithm of this. Here, okay, so I'll start by picking, say, this point. This will be C1. I picked this arbitrarily. Okay? So now I need to pick the furthest point away from this. What do you think? It's maybe this one down here, right? So then I pick C2. Now it's a little trickier, but what I want to do is I want to draw this Voronoi diagram. Again, so I draw this Voronoi diagram, which now just splits the data points by a hyperplane. And I happen to go through this point, but let's say it's on that side. Okay? So in general, they're probably not going to go through the boundary, but then you can assign it to either point. If it's right on the line, that means it's the same distance to either point. So it doesn't matter what side you put it. Okay, and now I need to find the furthest distance from one of these points, from one of the data points to one of the centers. And it's all of these points and these are close to one of the centers. So I'm going to tend to pick one of these points over here. And I think the furthest one is this one that goes right through the line. So now this one will be C3. And then I can draw the Voronoi diagram like this. Okay, so then this is the Voronoi diagram after 3 steps. I just keep picking the furthest point away. And this looks like it did a pretty good job. There were data points here, here, and here, and it found centers in each set. I did fairly well. Yeah.
And K is something that we determine.
Yeah, K is usually given on the input. If not, one thing you can do is you can run this algorithm for a larger K and look at the cost. And kind of there's this elbow technique where this is the value K and this is the cost function. And the cost should kind of come down like this. And so probably picking something around here. The cost is not going to get too much lower if I run it again. I'm just going to pick this point, and the furthest distance is going to go down not by too much, where picking this point, it went down by a lot. Right? So you're going to kind of drop off really quickly and then kind of level out. So you can run longer and then kind of go back and say that was the right K. Otherwise, it's just given as an input. Yeah. Okay, so this is the algorithm. It's very simple. You can do it in the runtime. How long does this take to run? Yeah, so you can do this in KN if you're smart about it, right? So the slow part here is, so I mean you have K times you go through the step 2, right? So there's a factor K there. And then you have to take this arg max, right? So you're looking at the maximum distance here. But you don't want to, the thing is, this argmax includes this nearest neighbor cost inside of it. So you don't want to recompute all these nearest neighbors every time. Most of them stay the same, right? Each of these data points has the same nearest neighbor as before. And so actually their cost is the same. I don't want to have to recompute its cost. I only want to update the cost of these data points which are closer. And so if I know the old assignment, if I keep track of where the data points are assigned, when I have a new center, I just need to scan them. After I choose a new center, I need to scan them again and update their cost. Right? And then this will allow me to quickly pick the next one. And so you can do this in kn time. I have k squared n in my notes, but I think you only need to do it k times. Yeah, you should only need to do it k times n time. You have to do 2 scans of the data for every round of k, but each of those scans take a whole event. Does that, people roughly see how that works? I've written out some pseudocode in more detail in the notes online. So if you want to implement, you can implement in k times n time. So it's pretty quick. I mean, this is compared to these hierarchical clustering algorithms that, if we were really careful in some cases, we could get them to be n squared log n. Now it's basically linear time, k times n, because k is usually much smaller than n. Right? So this is a much faster algorithm. Okay, but what strange biases is this going to have? What is the effect of running this? Well, okay, let me ask a different question. I said my goal was to minimize the longest edge. This algorithm is not guaranteed to minimize the longest edge. I just ran it greedily, and then I said, okay, that's good enough.
I think if you had a bunch of data that was in a circular area, you'd end up picking, you might start out at the center of that circle, and then you just start picking all the points around the edge of the circle or something, kind of alternating.
Yeah.
You wouldn't really, I don't know if that would really help.
Right, well, so it turns out, I mean, what you have is the right intuition. So let's say that, so let's think of a data set where I'll draw a circle first, and then I have all these data points inside here, including points on the edge of the circle and some in the middle. And so let's say I first picked a point here in the middle, then I'm going to pick a point on the edge of the circle, and then something far away in the edge of the circle. I'm going to keep picking these points here. Eventually, it's going to be, instead of picking this point, it's going to be further to pick, some point here. That'll be further from a point on the edge. Eventually, you'll start pushing back inside again. I mean, if your data looks like this, I don't know why you're having so many clusters in the first place. Again, if it's well clusterable, this will probably pick a center in each of the clusters. But yeah, so one property though is that initially, and this is true even if you do have clusters. Let's look at another example here. Let's say that my data points are kind of in these circles. What I'm going to do, the first one may be arbitrary, then the next ones are going to be kind of on the boundaries of these circles. I would rather have these move into the middle here. It's going to make, they represent the data better if they're kind of central to their cluster. This case centering algorithm is not going to pick something central to it. It's just going to, or the Gonzalez side, it's just going to pick points kind of on the boundary. But that's not so bad. As long as you divide them into the right sets, that's probably okay. If you want the model to be better, then there are other algorithms you could run maybe as a post-processing step or instead of this. And the k-means algorithm is going to be one of those. So or the Lloyd's algorithm for k-means, we'll talk about that next. And so, in fact, you should be able to see that if I move the center to the middle here, I should get a smaller furthest distance, right? If I considered this point over here, it's closer to this x than it was, it's closer to this x than it was to this other data point. So I'm actually making my objective smaller by centering these. So what this algorithm says is that this algorithm has the property that it's going to be a 2 approximation. So that means it's going to find a set of centers such that the cost infinity of the centers it finds is going to be less than or equal to 2 times so where this is so if C star are the optimal centers, then I guarantee the centers I find by this algorithm are going to be within a factor 2 in cost of the best possible. So this is not too hard to show. I might ask you to show this on the homework. This will be true for as long as the distance function is a metric. If the distance function is a metric, then this is going to be true. So I might ask this probably like a bonus question type sort of thing. But it's not too hard to show, and it's just a few line proof. So it guarantees to get close to the optimal cost. So how about an algorithm that does better? Can we do better than a 2 approximation? How would we do better? I think maybe doing the step where we centered them after we found the clusters. It turns out that it's NP hard to do better than a 2 approximation in general for inside any metric space. So NP hard to get a 2 minus epsilon approximation. So it's for any epsilon greater than 0, so to get a 1.99 approximation, that's NP hard, it turns out. Now, if you're doing this, there are a couple caveats to this. If your data is in 2 dimensions and you're using Euclidean distance, you can get like a 1.87 approximation in that case, something like that, using a much more complex algorithm. Okay, that's not really a big deal. I would still probably use this. Difference between a 1.87 and below that again is NP hard. But if your data is well clusterable, then this probably works much better than a 2 approximation. So it's just that there are some special cases where in general you can't do better than a 2 approximation. So you might as well use this algorithm if this is your objective, and maybe a little optimization. Again, very simple algorithm, very scalable. The only downside is that it requires the previous round of the for loop to complete before you do the next one. So if you want to do this in parallel or something like that, then it's not clear how to do that again. But otherwise, it's very efficient if your data, if you can allow k rounds, if k is small. Okay? It's actually a pretty cool algorithm. Okay, let's. Okay, so let's talk now about Lloyd's algorithm. For k-means. And so this is a tribute to Lloyd, and he apparently came up with this in 1957, but he didn't publish it until 1982. Apparently wrote it down someplace. It was never officially published, and finally someone said, you should go and officially publish this. But it took, what was that, like 25 years. Right, so it's a long time. Again, it's going to be a very simple algorithm. It's going to be a little more, it's not going to be purely greedy like the K-center algorithm, like the Gonzalez algorithm. So let me write this down and then we'll talk about it. So instead of, in this algorithm, instead of choosing one center at a time, I'm going to kind of try and choose all K-centers at a time. But I know I'm not going to do it right the first time, so then I'm going to try and fix it and then keep fixing it. So I'm going to choose K points C as a subset of X. And so maybe this is going to be arbitrary. So arbitrarily choose K points. And this is going to be my initial set of centers. Again, I'm no longer building up these centers. I'm always going to have exactly K centers. And so now I'm going to repeat the following process. So there's going to be two steps inside of here. For all X and X, define phi. Right, so this is going to be to assign or reassign to the closest center. Okay, so in the first step, I just have the centers and I assign everything to the closest center. I haven't done that yet. And then in this step, for I in the set K, so for each cluster or each center, I'm going to reassign the center to be the average of SI, of the set SI. And remember, this is the set okay, so again, I'm going to average based on the set assigned to the center. This is all the data points where their closest point is the same center. Okay, and then I'll run this, say, until say it's converged, and we'll talk a little bit what that means. But at some point I'll stop. Either when things stop changing, or maybe I'll stop before that if things are changing but very slowly. Okay, so in order to compute the new center, I need to know the center assignment. I need to know the set of all the data points in the center. Right? And then given the set of centers, I'm going to recompute. This defines the set of centers. I can recompute the assignment of the points. And each time, the center is an average. Right? It's going to give me an average, so it's always going to be in the middle of all the points in my data set. Right? So I'm not going to get that example like up there where the center is on the boundary. Every time I run this step, I'm going to remove this data point into the center here. Okay, so let's look at some of these steps in a little bit more detail here. What do I mean? Let's look at this step. Average SI, right? So this is, if I take this set, so I want to recompute the center here. I have a set of data points. So now I figure I have this set, and I know, and I actually don't care where the old center was. I want to create the new center here. I want to create the new CI from this set, SI. But the average, well, the nice thing about the average is that I can do it one coordinate at a time. So I can basically look at the average x coordinate and also look at the average y coordinate, and that'll give me the overall average. Right? So so this is basically 1 over the size of the set times all the data points in here, and I look at, well, x was a right choice. So c dot x, so this would be c lowercase x, all s in this set si. I'm going to look at the x coordinate, right? I can take this set, look at this guy's x coordinate, and I average the x coordinate. That gives me the x coordinate of the center, and I do the same thing with the y coordinate. Do these independently. That's one of the nice things about the average. It's one of these things that's I can do this coordinate independent. If I rotated the coordinate frame, this is actually going to give the same answer. So that's one of the nice things about you working in the Euclidean space. The other thing about this new center I is if I do take this average, I calculate the average of all the other points, it turns out that this is equivalent to choosing Ci equals the R min of some point Z in RD. That's minimizing the sum of the squared distances. Okay, so the average turns out minimizes the sum of the squared distances to all the other points. Not the sum of the distances. That turns out that's called the L1 median. The average, which is very easy to compute, right? I just take the average of the x coordinates, the average of the y coordinates. That's giving me exactly the minimizing point of the sum of the squared distances, which was my objective function. That's why I wanted this as my objective. I wanted this as my objective function for k-means. This has kind of been a point of confusion. There's been some pretty funny points in history where there's at some point there was I think the U.S. government asked someone to track the points in the U.S. that minimize the sum of all the distances to all of the residents in the U.S. based on the census. And so they computed the average, which was not minimizing the sum of the distances. It was minimizing the sum of the squared distances. And so if you know how the population of the U.S. has changed over time, it's actually had these outliers in it, right? There's some people all the way up in Alaska, and it started all on the East Coast, and people moved out all the way to California or Utah on the way out there. And so there was a fairly big difference between the sum of the squared distances and the sum of the distances. And so they had this wrong by like hundreds of miles. I don't think it mattered that much, but I think they still track what's called the L1 median, and I think that's now in the I think it's like in somewhere around St. Louis, but it's been moving further south recently. You can see some charts of this online, or sometimes they'll track the average just because that's easier to compute. Okay, so this average step is really easy to compute. It gives something which is really in the center of the data set every step. in the center of the data set it's trying to approximate. And so this algorithm is very simple, very easy. Every step is not hard to do. The 2A step is to find the nearest neighbor. We already talked about doing that. In most data sets, people do this exactly just by checking because the set of centers is often small. But if your set of centers is big, then you can use one of these data structures we talked about before. You have to rebuild these data structures, so it's not clear you're going to get that much of an advantage doing that, but you could in some cases. Okay, so let's talk about the convergence. Is this algorithm going to converge to the right answer? Is this going to converge? Is this, like, I'm doing kind of two things. I'm reassigning centers, and then I'm reassigning the points to each center. Like sometimes when you run these iterative algorithms, there can be a situation where you get into an infinite loop, where you assign the center over here, and then you think of, you have 3 centers and they keep kind of shifting or rotating, and the assignment kind of moves with them. Right? Is this algorithm going to kind of, is this going to get into an infinite loop? Is this going to converge to the right answer? How many steps does it take? What's going on here? What do people think?
Converges where you don't get the right answer necessarily.
So what is it? So it converges. So how do you know it converges?
You asked me to guess and
Okay. Okay. Well, so that's the right answer. Good. You maybe have either great intuition or inferred from the multiple questions I was asking. But yeah. So it converges. That means it's not going to get stuck in an infinite loop. Otherwise, we wouldn't be talking about it. But it may not find the true minimum, right? Again, like the k-center problem, it may not actually find the ultimate optimal solution, right? It may not give the right answer. In fact, it may get stuck in some situations where neither of these steps changes the result, but there's another solution which is better. Let me try and draw an example here. So you could get in a situation, let's say you have some data here, some data over here, and then some data over here, and you're given 3 centers. And if I choose one center here, one center here, and one center here, what's going to happen is my Voronoi diagram is going to look like this. And then it's going to look kind of like this. This is my Voronoi diagram. And so each of those red centers is in the, it does not want to change. It is the average of all of its data points. Or maybe I can move this one down here. So it doesn't have to be one of the data points. I move that one down there. These are all the average of all their data points. And each data point is in the right Voronoi cell. But clearly, there's, you know, if you look at this, there's another solution which is going to do a lot better, right? The blue one is going to give a lot better cost, but the red one is a local minimum. So the algorithm is not going to find the blue one like this. So if you get the center stuck in the wrong place, you might get stuck there. Okay, so it may not reach the global maximum. What you should probably consider doing is try with the different sort of initial centers, and we'll talk about that in a second. And then rerun it again, and probably eventually it will find the right solution. If it gets close to the right solution, it will converge to it. But if it gets stuck someplace like this red situation, then it might not be able to get out of it.
Well, so it does converge?
Well, it converges to a local minimum,
Yeah.
meaning it stops.
How do you, is Is there proof for it?
Yeah, right. So the question is, how do you know that it's going to stop? And so the way to think about this is to go through the cost function. Right? Remember our cost function. Remember we have the cost of xc is equal to the sum over x and x of squared, right? So this was our cost function. And the proof is to see that both of these two steps, they only decrease this cost function. Okay? If I'm assigning a different, if I'm assigning a point to a closer center, I can look at that individual point. This term in the sum decreases. Right? So that the step 2a has to decrease this cost function because I found a better nearest neighbor cost here. Okay? And the averaging step, it's exactly this arg min. It returns the center, which minimizes the sum of the square distances to all the points in the set. And if you remember, I rewrote, I said up here that you can rewrite the k-means cost, the sum of over all the centers, times the cost in that center, in that cluster, right? So those are equivalent. I've just broken up the sum into parts. And so I've minimized each of these inner terms every time I did that centering step. If I've returned the minimal center for that, the cost must not increase at least, right? If it's the same center, then the cost hasn't, then the cost hasn't decreased, but hasn't increased either, right? So that means every step A or B here, I am decreasing this cost function. Okay, so what that means is that I can't possibly have at any step the same set of centers, or if I do, then I know I have the centers haven't changed and I can stop. Or kind of the centers is this, these can be continuous. They really could be anywhere in the space. But the set SI, these clusters, this is a combinatorial set. There's a finite number of possible ways of breaking up the data, of partitioning the data. It's a lot. It's like, what is it? It's n. It's k choose n different ways of breaking up the data. No, it's not k choose n. It's k to the power n ways of partitioning the data into k clusters. But that's finite, so I know it'll eventually stop. You know, there are. So why can you see there are k to the n? Why can there be k to the n possible clusters? Well, the way to think about that is you have n. So there are n of these data points, and each of these you can think of storing. And this is actually a good way to implement the algorithm. You have an array, and the array goes from 1 to n. And in each element of the array, you store a value between 1 and k, right? This is either 1, 2, 3, up to k. So in this array, that's from each data point mapping to a cluster, it's a value 1 through k. And so if I can choose k possible locations here, k there, and so forth, each of them has k independent locations it can be, or assignments it can be. So there are k to the n possible clusters. So it's finite. It will eventually, every time I do a new assignment of clusters, I get a different array here. And every step along that assignment, the cost decreases. So it eventually is converging. The cost is going down at a certain rate. So, you know, so there are a couple ways to deal with this problem of at what point has it converged. You could say that those two arrays that you have of the center assignments has not changed in between the steps. But what kind of sometimes happens is you start getting very small movement where if you're, for instance, if you're in a situation like this bad case, but you have two centers and there's a big cluster right here, you may kind of move these around very slowly with some very subtle rearrangements. And if you're more than 2 dimensions, then this kind of can sort of happen. And so you don't want to, so you may not want to run till it completely stops. And also that's a little bit trickier to check. You kind of want to, you store your old array and then check if it's exactly the same as before. Maybe you can just keep a bit of whether any of the centers was reassigned. But the other way to do is just to keep track of the overall cost. And if the overall cost is changed by a small enough amount, then you can stop. So that's more common. So that so if cost change is smaller than some so it's smaller than some threshold. So set some threshold for the difference between the cost values, or maybe some relative changes, change less than 1%. Say, okay, that's probably good enough. Or maybe you just say run for 20 iterations. Usually 20 iterations is more than enough on most reasonable data sets. Okay, so assuming you started with a good set of centers, right? Let's go up and let's look at this top line here as well. Assuming I start with a good set of centers, it's a pretty easy algorithm. It's guaranteed to converge to a local minimum. But if this first set of centers is fairly reasonable, then this works. It gives centers very representative of the data inside their cluster as well. So that's why this is such a popular algorithm. Very easy to use. Generally works well. If the data is well clusterable, this should generally work well. If they're nice, well-defined clusters. Okay, so, but there are examples like these. This is kind of, this red example is bad, right? This is not what you want. And so if we're in 2 dimensions, we can like plot this data and we can look at it and we can say, yeah, these red centers are not what we want. But if you're in 2D and you can plot it, you can also just circle the right centers and be done with it, right? So, so this is useful in higher dimensional data where you can't really see what's going on so much. You may not know that this has happened. If something bad like the red center assignment has happened. How would you prevent this from happening?
You just pick random starting centers over and over again and compare the results. I'm not really sure how you figure out which one was better.
Yeah, so
overall, maybe.
so how to choose the so the initial C centers. So one choice is random, right? So if you've chosen at random, and then you run it, and you can compute the cost really easily. The cost is kind of almost naturally computed as you're doing it. So then you can compare the cost. If one cost is much lower than the others, then you take that solution, right? So compute C centers, run it for 10, 20 steps, and then try it again and keep whichever one has the lowest cost. So keep lowest cost solution after, and it's important to do this after running Lloyd's algorithm. So don't pick case centers and then choose one of them based on its lowest cost. Use it, run Lloyd's algorithm for a few steps, and then pick the lowest cost. That'll work much better. So random is a pretty good idea, but if I have this situation, and say I have about a third of the points in each cluster, then it's not too unlikely to pick 2 points in the same one, right? So if I pick the first one over here, the second one over here, then about a third of the time, the third one will be over here. And so, you know, if you have more clusters, if instead of 3 clusters you have like 20 clusters, k is 20, and they're all kind of in a situation like this symmetrically, then the chance that you get 1 point in each cluster might actually be pretty low. This goes back to the coupon collector problem, right? You'd expect to take about k log k samples until you pick 1 point in each cluster. Well, so if we know that about coupon collectors, then why don't we pick k log k samples? And then we can cluster with k log k instead of k, and then regroup together the centers. So run Lloyd's with k log k centers, and then try and regroup these. And then you can use like hierarchical clustering. You only have k log k data points, not too many. You can then kind of merge these together until you get k. Regroup with hierarchical agglomerate clustering.
What's the runtime for Lloyd's algorithm?
It's the number of steps you run, so the number of times through the for loop, which may be 10, and each step takes n. It depends on this nearest neighbor problem, right? You need to reassign to the nearest neighbor. So the averaging step takes linear time. Even across k clusters, you divide up the cost. The assignment to the nearest neighbor, you may need to use an advanced nearest neighbor data structure to run that. But they're only k centers, so you can just check each one against the k. So this step is at most O of k times n, and this one is O of n. You can check, they're only, k is fairly small compared to n, so you're probably okay running k on that. And then number of loops is probably a constant.
So the disadvantage of using k centers is that you pick on the perimeter of the clusters.
Yeah. So
why not use k center to pick the first round?
Good, yes. This was another answer I was looking for. Use Gonzalez. Use the Gonzalez k-center algorithm. Right? So this is another good idea. Using Gonzalez k-center, it will enforce that you are not too far from any point. Right? So it will never wind up with this solution here. It won't wind up with this because, you could have picked a data point here, but probably neither of these points is further than any point here is to this one, right? If not, then it probably doesn't matter so much. If it's not that big a difference, then these two kind of look like one cluster anyways. Right, so if we use the k-center algorithm, we're going to avoid this situation. So it turns out that the k-center is a good idea, but there are some tricky situations where that one doesn't even always solve. You can still get into some problem cases. Okay, so to get around this, there is another algorithm called k-means ++. And so this is going to work. This is going to work similar to the Gonzalez algorithm, but is more tailor-made to the k-means cost function. Okay, so let me write this down. Choose C1 in X, and so the first one is arbitrarily, and again I'm going to maintain this set of centers. So this is for the first I centers is in the set. And so then for two, then I'm going to again do a for loop to k. And now I'm going to, This is inside the for loop. So I'm going to choose CI from X with probability proportional to okay, so instead of choosing the one that's the furthest value here, I'm going to choose one proportional to this distance. So the ones that are further, I'm more likely going to choose. Okay, so instead of biasing towards really far away points, I'm going to choose points that more likely are further away. The problem with k-center is that if there's one outlier data point, I'm going to put a cluster center on it. I'm always going to choose that one. Now, it turns out for a lot of these formulations, sometimes that is the right thing to do. Sometimes it's not the right thing to do, and there's kind of some boundary case where it's far away enough to be an outlier, but not far away enough that you really need to put it as the center. And so this will it will sometimes pick an outlier point, but it will more likely pick some point around where there's a lot of other data points. And exactly proportional to the cost function you're trying to minimize instead here. And so you still may need to run this a few times randomly. This is a randomized algorithm. I'm choosing with probability proportional to this distance. So I may need to run this a few times because sometimes it'll still pick that outlier, which is bad. But it will only pick it very likely if it really needs to be a center by itself. Okay, so we started a bit late, and there were two more things I wanted to talk about. So I'm going to talk briefly about, and both of them are brief. So I'll talk briefly about one, and then I'll come back to, there should be something here. I'm going to choose this proportional to this distance. How do I do that? How do I write an algorithm to do that? I'll come back and tell you in a second. So if you need to go at 4:20, I guess you'll have to watch the video. Otherwise, I'll spend another 5 minutes doing that. Let me say something about the k-median and k-medioid cost versions here first, just for a minute. As I just started talking about, the k-means is susceptible to these outliers. It's more likely, if there's an outlier point, to say, I really need to put a center there, even though there's nothing else around there. The k-median, because it's only the sum of the distances, not the squared distances, which makes the outlier even more important, it's more likely to pick a center within the actual data set. So this is more robust to these outliers, the k-median formulation. The other thing about this Lloyd's algorithm is that there's this nice way I can take the average, which minimizes the cost, the sum of the squared cost to all the points in the set of the centers. There's not a similar closed form solution for the k-median. There's something called the L1 median or the geometric median. That is the point that minimizes the sum of the distances. But there's not a closed form for that. There is an iterative step you can do instead. So inside of the iteration of reassigning the centers, you can, to find the new center for a cluster, you can iterate towards that. And it's a pretty easy update step. And so you run that for a few iterations, and that always decreases the cost. And then you go back and reassign points to centers, and you repeat. And so you can fit another step inside of here. But both of those things, both of those iterative things that are guaranteed to converge in that way, they need essentially the data to be using the Euclidean distance. Some of these you can adapt to some other manifold structure, but in general you need the Euclidean distance. If you don't, if you're using like the Jacquard distance instead, because you're taking the distance over sets, then there's not a notion of what is the average of a set of sets. I don't know what that average is anymore. So then, instead of that, you can choose the center as one of the data points. Right, so we discussed this a little bit in the hierarchical clustering. But this is called the k-medioid. So often you use this if you would use this instead of the k-means formulation because it's more robust. And so use this if your distance is not the natural Euclidean distance. Then you'd probably want to use formulation of this. And if you look in MATLAB, I think it has a k-means built-in thing and a k-medioid. I don't think it has a k-median, because you usually want to use this one or that one just for speed. Okay, so there's some other cool stuff about this that I won't get into. You may want to know how to implement this on your homework. So maybe I'll tell you how to do that. So I'll finish this just in a few minutes, and then you can ask me more about it later. And maybe another class, if I have time, I'll discuss this again, because it's a really cool thing that comes up over and over again. So start by saying, what's the sum over all these distances? Right, so I can compute a sum, and let's call this let's not use sum, let's call this m, and this one is called mx, right? So this is, so just this distance for the x data point is mx, right? So if I calculate this sum, then the probability of choosing x should be equal to mx over the sum, right? So now, instead of choosing proportional to this distance, I can choose with this probability that I've calculated, okay? And so this is the value between 0 and 1, right? And the sum of these have to add up to 1, because I knew the sum of all the mx's added up to m, and I divided through by a big M here. Okay, good. So the next kind of thing to realize is that what I can do is I can take this probability space, and I'm going to think of carving it up into chunks. So this is mx1, this is mx2 is in this chunk. So say this was like 0.07, this is 0.09, this is mx3 up to mxn. It's in this chunk, right? I've divided up this probability space, and so now I have this built-in thing where I can choose a random number u between 0 and 1, and this random number is going to index into one of these values. So I've divided up the interval between 0 and 1 with these probabilities, and I can generate a random u, and wherever that lands in here, the bucket that it falls into is the element I choose. Okay? So if you've you've divided up this, and you can do this by just, so this threshold right here, this threshold, which is the end of mx3, this is equal to the sum of I equals 1 to 3 of mxi, right? I just added up all the probabilities up to this point, right? So that tells me where that endpoint is. Okay, so I can calculate, if I calculate each of these probabilities, and then I can calculate the endpoints. This is basically something like a cumulative density function, although there's not really, the ordering is arbitrary, right? So then if I want to do this, I can mark these boundaries, and then if I pick this u, I know it falls in between these two endpoints I've calculated, then it goes there. So one way is just to scan across just kind of, there's some ordering, and I keep checking, is U greater than this one? Is it greater than this one? When it's greater than it, then just double check it's less than the next one. And then if it's no longer greater than this one, then I know I've hit the right point. I can also do something faster. If I have this thing with these boundaries here, right? I can build a binary tree on top of these. Right, I can build a binary tree on top of these values. And so then if I have some value U that's coming in, I can walk down the tree in the bucket. So then this only takes log n time if I have n data points. So this is a faster way to do it. Okay, so this optimization, for really big N, it actually makes a big difference. If you pick a lot of random things. Although this is going to change every step when you're running this k-means plus algorithm. And so you can just rebuild this and do a scan because you just need to use it once. There's another cool trick called the aliasing trick, which uses hashing, which allows you to do this in constant time. That if you come and ask me after class about that. Just one more thing about this k-means plus algorithm. It's kind of, there's some sort of guarantees about it that say that if you run this randomly a few times, and either it's going to give you some guarantee of how good you approximate the k-means objective by running Lloyd's algorithm afterwards. There's some guarantee for any data, which is like a log n guarantee, or a constant factor guarantee like you got for the k-center algorithm, assuming the data is not too crazy. But it can guarantee that you don't do things bad, and it actually works better. The k-means plus algorithm is maybe 10 years old now, and it's kind of the accepted way to pre-process the Lloyd's algorithm. So that was for assignment-based clustering. We'll talk about spectral clustering next week, Wednesday. It's going to be kind of a completely different way of approaching this problem. Great, thanks. Yeah, question.
So the number of bins that you have, is the width of your bin just 1 per n?
If all the things are equally likely, then that's going to be the case, right? But you're going to do it proportional to this squared distance from the center. So some of them you want to pick more likely. If I go back up to something that looks like this, say I pick one of these red points and this red point, then all of these are closer. They're squared distances. So let's say I just picked one red point here. All of the points over here are going to have a very small squared distance. All of these are going to be very large. So very likely I'm going to pick one of these points as the next center. Either here or there. They're all going to be about the same distance.